Good evening, everyone. Today I'm going to talk about the lessons learned while scaling Elasticsearch at Vinted. Before I begin the talk, I want to thank Vinted because it allowed me plenty of opportunities to solve really difficult technical challenges. I also want to thank Elasticsearch for inviting me to give this talk at their meetup. So let's go into the presentation. So the first things first. So who am I? My name is Dainius Jocas. I work at a company called Vinted, whose mission is to make the second hand the first choice worldwide. I'm a staff engineer there, and I do have some web presence. I have my personal website. I do have Twitter, and also I'm the author of an open source search tool, SceneGrab. Check my GitHub for that. So today, I'll do a short introduction into what I'm going to talk about. Then I'll describe the scale of Elasticsearch installation at Vinted as it was around January 2020, so a bit more than a year ago. Then we'll proceed with 3 lessons learned, and those lessons are going to be small enough so that I can fit them into presentations such as that one. And those lessons will be that your IDs should be as keywords. Be careful while working with dates in Elasticsearch. Then we'll have a chat about the function score. And after the lessons, I'll talk about scale of Elasticsearch as of January 2021, so a couple of months ago. And then we can go into discussion where I will be available to answer hopefully all of your questions. So, introduction. So, Vinted and Elasticsearch. So, as mentioned previously, Vinted is a second-hand clothes marketplace. It operates in around 10 countries, and in those 10 countries, unfortunately, we have 10 different languages, since Vinted operates mostly in Europe. So, the first installation of Elasticsearch, as I checked in our chef repository, is since 2014, and the first version that was installed was 1.4.1, so quite some time ago. And yes, so today I'll share some lessons learned while scaling Elasticsearch at Vinted. Yeah, so let's go with deployment details. So a year ago, we had running Elasticsearch of version 5.8.6, which was almost end of the life at that time. We had a monster installation that was of around 420 only data nodes, that each of the data node had 14 CPU with 64 gigabytes of RAM, and everything was installed on bare metal. And as of usage, it had at peak times, at peak hours, around 300,000 RPS per minute. What do I mean by peak hours? Peak hours are evenings from 8 to 10, and the highest peaks during the week is Sunday. And at the time, our main indices had around 160 million documents. And some interesting numbers also from that time is that the main search always hit 84 shards with 4 replicas. And with such a setup, we were able to reach P99 latency during those peak hours of around 250 milliseconds. Of course, we were measuring the slow log of Elasticsearch, and by slow log, we set queries whose latency is more than 100 milliseconds. And those slow log queries skyrocketed during the peak hours. So that's the state of deployment. And how was Elastic seen from the company perspective? So from the company perspective, Elasticsearch was seen as a risk because backend developers didn't want to touch it. Because Elasticsearch was perceived as a complicated system back then. However, the usage of Vinted platform was expected to at least double by October of 2020, so in 9 months. And a similar increase in usage was expected for Elasticsearch. And as I mentioned in the previous slide, we had a monster Elasticsearch installation that was barely keeping up with the load at that time. And adding more servers to that cluster was considered a bad idea. So what led to such a bad situation a year ago? So it just happened that over the years, the functionality on top of Elasticsearch just accumulated with no oversight and no clear ownership of the features there. What's more, at that time, SREs were responsible for keeping Elasticsearch operational during the duty days. And as a hint of that situation, server restarts, the usual cure from the SRE, doesn't help all that much when Elasticsearch clusters are overloaded. Just to illustrate how dire the situation was at the time, so it was January 2017, and I was just started at Vinted, and I did a little experiment by replaying 10,000 queries from the slow log back into production Elasticsearch cluster, just to have a look what happens, how is it working. And those 10,000 queries that were shot over, I don't know, a 2 minutes or 3 minutes time caused 4 million slow queries, as you see in this high bar in the middle of the day. So the situation was that dire, that a little increase in the query traffic might bring the Elasticsearch on its knees. So that's it. That was the situation. So let's go with our adventures and lessons learned. So the first lesson I want to talk about is that it is important to store your ID data as keywords in Elasticsearch. And by IDs, I mean, if your workload that you want to support is simple Boolean filtering on some terms in Elasticsearch, simple terms queries on some IDs, you should store that data as keywords. And for a little context about this problem, at Vinted, Elasticsearch indexes the data from MySQL. On the details how it's done, you can check Vinted engineering blog for that. But just the thing that you really need to know is that it's a common practice for Ruby on Rails application to create database tables with primary keys of those tables as auto-increment integers. And and we can play now a little quiz here. So how do you think? Which Elasticsearch data type for the fields that are going to accommodate those integers should be? If your answer is integers, because why not, then I hope that in the next slides I will show you that you've been wrong. So the story of IDs as keywords. Sometime in 2016, there was a blog post in Elasticsearch engineering blog which was about the evolution of numeric range filters in Apache Lucene. And just the TLDR version of that blog post is that before this change, integers were indexed as padded string terms into the index. And after the change, the integers were indexed as block KD trees, or BKD for short. And this change in Lucene got into Elasticsearch since version 5.0. This basically meant that numeric data types were optimized for range queries. Things like, give me all the things that are from 5 to 10. And however, this new functionality didn't break the existing functionality, meaning that numeric data types still supported terms queries, which is nice. But however, from the Vinted engineering point of view, when we use IDs, when we query ID fields, we don't do range queries on them. We use IDs for simple term filtering, as seen in the example before. So what happened is that the optimized integer data type for our use case actually degraded the performance for us. But by how much? So when we ran the experiments with our query load some time ago, we noticed that we can decrease the query latency, P99 latency, by around 50%, which at that time resulted in around 20 milliseconds, which was huge, considering that that only the required change was we just changed the data, the index mappings, and re-index the data. That's it. Work is done. So that was a huge win with very low effort. So yeah, that was the first lesson, that ID should be stored as keywords. And to summarize it, that it's worth mentioning once again that Vinted started to use Elasticsearch pre-version 5.0. And at that time, when the Elasticsearch was version 1 point something, it was okay to use integer data types for ID fields. However, post 5.0, IDs as integers became a performance issue, the silent performance issue, which I would argue that's such a change that actually breaks nothing, just improves things somewhere in one places and degrades performance in some other places, can easily slip under the radar of regular developers, and this change could backfire badly sometime after. And what was the outcome? As I mentioned before, regular developers, the backend developers of Vinted, thought that Elasticsearch is just a slow search engine, which was caused by unfortunate circumstances. Yeah, so my advice is store your IDs as keywords in Elasticsearch. Yeah, so that was the first lesson. As for the second lesson, I want to talk about some common issues that you can find when you're working with dates in Elasticsearch. So I'm going to talk about two aspects there, about the date math and date filters. Okay, so what's this date math thing? As you see in this red box here, there's written things such as now minus 7 days. And the intended usage of this example query is that I want all the documents from Elasticsearch index that were created during those last 7 days, starting to count from now. So, what are the issues with this type of approach for date queries? Most queries that use now, meaning date math, cannot be cached, and as most of us that work with Elasticsearch know, that caching is the #1 reason why Elasticsearch performs well, and we need to leverage all the caches as much as possible. However, from the developer's point of view, using date math is simple. You just hard code the constant now minus 7 days, and that's it. Your task is done. The document, the hit set is limited to only the documents created during those last 7 days. Life is easy. However, if most of your queries are using date math, then CPU usage is very high, because for every query that you issue into Elasticsearch, this little filter clause has to be computed over and over again. And having more traffic, the whole Elasticsearch cluster might start to have a so-called hot nodes problem, meaning that a couple of nodes are just queuing the search requests and returning 504s, meaning timeouts. So when thinking about using date math, my advice, always use timestamps, exact timestamps in production. Of course, the advice is for production use. If you're just playing in Kibana, date math is fine because it's easy to read and it's good enough because it's just one or two queries overall. However, in production, use timestamps. And the primary reason is that if you use timestamps, queries get cached. These filter clauses get cached, which turns out into massive gains in the cluster throughput because of properly using the cache. Yeah, so okay, so let's go into a bit more nuanced topic, which is filtering on dates. So this example is very simple, similar to the one that we've seen previously. However, we still have this filter that filters on created at, but at this time we have an exact timestamp, and we want documents that were created earlier than this timestamp. So let's discuss this date filter in a bit more detailed way. So what this query clause asks Elasticsearch is to collect all the docs that are not newer than X timestamp. But think about a situation: what if the X, this timestamp, is meant to be now, meaning the current timestamp, and your documents in the index are accumulated over the last 10 years? Then this filter will match 99% of all the documents in your indices, and by 99 it's just a very high percentage, meaning almost all. And I would argue that such a filter is not a good filter. And let's see how to make it better. So I would argue that if we would invert such a clause into an equal clause from the logic perspective, which would change the filter into must not, just to invert the clause, and then we use the same timestamp. It's just that we say that the greater than this timestamp. So that's the query that got rewritten. Basically, what this query says is asks Elasticsearch to collect all the docs that are not newer than X timestamp. And if the situation is similar to the described previously, this means that when the X is now and your documents are accumulated over the period of 10 years, then this filter from previous slide will match something, a very small portion of index, meaning some like 1% of your documents. And I would argue that it is a good filter because it's very specific, and Elasticsearch likes specific filters. And if you read the documentation of Elasticsearch, paying a good amount of attention, you will find such a brilliant piece of advice that if you must filter by timestamp, use a coarse granularity. Example, round the timestamp to 5 minutes or whatever the time period that is appropriate for your use case, so that the query value changes infrequently. So by rounding the timestamp, I mean not including the seconds or milliseconds into the timestamp string. And when we tried this trick, just to invert the clause from documents not newer than something into the clause that don't give me documents that are newer than something, we reduced our P99 latency by around 15%. And at that time, it turned out into the decrease in latency of around 10 milliseconds. And when we deployed such a trick, we looked at the dashboards and we were excited because we clearly see that we decreased the P99 latency significantly. And it was a very simple change because it required us just to rewrite the query and nothing else. So nice results. And And once you see dashboards as seen in the previous slide, you feel good. You feel sense of achievement. Yeah. So date summary. So 2 lessons here. Don't use date math in production querying, and write filters on timestamp fields so that the filter matches fewer documents, whatever is your use case. Yes. So the third part, let's talk about the function score. The function score is queries such as this one. You just and Elasticsearch provides us with many functions, and here it is an example of a function score usage from a year ago, where we used a script score, where we scored our documents based on how recently the document was updated in our indices. Basically, what the query in the previous slide did was that it boosted hits of a query based on novelty, meaning that the newer the document was, the higher it should appear in the hit list. Why was it a good solution some time ago? Because the function score allows multiplication on this hit score, and multiplication is an easy thing to understand and to work on, because you can imagine that the scores are increasing in the similar fashion as you see in the chart at the bottom of the slide. So the x-axis here starts from the point in time which is now, and it goes in some milliseconds from now. So the newer documents are scored higher, and the scores of a hit are multiplied with some factor there. Looking at this query, you might ask a simple question: why you are writing a custom script score query when there are several default decay functions that would do exactly the same thing? The surprising thing that we've tried those decay functions, and the decay functions performed worse in our benchmarks than our custom script score query. So yeah, so what were exactly the problems with the function score query? So after the benchmarking, we clearly seen that this function score clause was the biggest contributor to the query latency, and the big problem was that the script was executed on every hit of all the other filters of that search query. And you can guess that the most problematic queries were those queries that had many hits. For example, the query that had 10,000 hits was just had very high latency. And was this situation very frequent for Vinted users? I would argue that the situation was frequent, because imagine a query which is a dress, let's say, or a red dress, where Vinted has million of those. And since this query is very frequent, we have a lot of expensive queries, and those expensive queries were contributing to the high number of slow log queries. So how we were fighting against those problematic queries and with the function score? The first approach was just to increase the number of shards. And sharding for some time really helped to keep the latency down. Remember that at the beginning of 2020, the main index had 84 shards for 160 million documents, meaning one shard had only 2 million documents around. But at some point in time, it turned out that sharding turned into over-sharding and no longer helped. So we had to find another solution. And the task was to come up with a way to replace the function score query clause with something that is more performant, but at the same time preserves the ranking logic. And this was not an easy task, I would argue. What we came up with was to introduce a distance feature query. Distance feature query is used to increase the score of a hit. That's why it went into the should part of the bool clause. And we use the same field for the distance feature query as we use for the function score query. And here we use origin exact timestamp. And we use some pivot value that was 7 days. That proved to be, let's say, similar enough to what the function score was providing us. However, the distance feature provided us a similar boost on novelty. However, it turned multiplicative boost provided by the function score query into additive boost, meaning that instead of multiplying the score of a hit from the base query clauses, we just add some score to the hit, which means that it is a significant change in the querying logic. So what was complicated was to find the boost values and the pivot values that would result in a similar ranking to the function score query. On the other hand, unlike the function score query, the distance feature query seemed to be better in terms of performance, because the distance feature query knows how to efficiently skip non-competitive hits, meaning that if let's say a segment or a shard contains only the old documents, then this distance feature query clause might not get executed at all. So meaning we have the top k hits without applying a costly function on every hit from the top k. And remember, we had those 10-year-old documents still sitting in our index and being exposed for the Vinted users. So that seemed as a good performance optimization. Also note that the origin value in the documentation of Elasticsearch is in the example is set to null. And remember from the dates lesson learned that it's not a good thing because of date math problems, because it fights against caching. Yeah, so basically what we've done, we've replaced the function score query clause with the distance feature query clause, and that was both the performance optimization, and it helped us to let's say to start playing properly with our scoring, main scoring of Elasticsearch documents. So, summary of the function score lesson learned. Function score provides really flexible scoring options. There are many functions provided, and it is multiplicative, which is good. However, when applying a function score on big indices, you must be careful. Because function score is applied on all the hits. Of course, unless you put the function score into the rescore query part, where you can say on how many hits do you want to score with a function score. But if your requirements are that everything should be scored, then you're out of luck. The function score will be applied on all the hits. Also, the function score has this problem that it has no way to know but if it can skip any hits from the hit list. So it has to go through all the hits. Yeah, and function score is not, let's say, a friend of caching. And once again, caching is the number one reason why Elasticsearch performance is good. And as a lesson learned, in some cases, you can change the function score query clauses into distance feature query clauses, and it will save you in terms of performance. Yes, so that's the function score. Yeah, so these were the lessons learned, three simple lessons learned of scaling Elasticsearch. And now, just for the sake of completeness, I'll share some numbers of Elasticsearch deployment as of January 2021. So now we run Elasticsearch 7.9.3. So we managed to upgrade almost seamlessly from Elasticsearch version 5.6 all the way up to 7.9 in a one step. So another deviation from the setup from last year is that now we have 3 clusters, each of which has 160 data nodes, and each data node has now 16 CPU and 64 gigabytes of RAM, and we are still running on bare metal. And we have one additional offline cluster of similar size as those 3 are, just for testing, meaning that we can test the Elasticsearch version upgrades before releasing those into production. Or if we want to try out some cluster setup, we have a big Elasticsearch cluster that we just can route queries into that cluster and just have a look at the numbers. And as of January 2021, during the peak hours, the evening hours, we had more than 1 million queries per minute. And this number is more than 3 times bigger than the number a year ago. So we had 3 times more traffic. Also, the number of documents in Elasticsearch index also grew up. It grew up from 160 million to 360 million. So more than 200 million documents that you can query with every query, and they need to be scored. Currently, our latency P99 during peak hours is around 150 milliseconds, which we consider good enough. This, with the new setup of Elasticsearch, we started to measure how many timeouts, meaning queries whose latency is more than 500 milliseconds. And as for the timeouts, we have only 0.03% of all the queries during the peak hours. During not the peak hours, the percentage of timeouts is even less so. Yeah, so that's the deployment and how it's seen from the organizational point of view now. Now the team that is responsible for keeping Elasticsearch up and running is 8 people strong. The team is doing a regular capacity testing and checking if the current Elasticsearch installation could handle the load, which is 2 times bigger, both in terms of document count and in terms of query throughput. Also, Elasticsearch from the engineering manager's perspective is seen as a system that can handle the growth, meaning that it is reliable and we have a good knowledge of it. One thing that got into our workflow in terms of releasing features on Elasticsearch is that functionality can be tested before releasing into production, meaning that we can evaluate how much of our, let's say, performance latency budget will be consumed by some additional functionality, or how much we would gain to removing some functionality or doing some optimization. And another nice thing is that the team that is working with Elasticsearch functionality is constantly on duty. So, and the engineers that are on duty are keeping, and their responsibility is to keep Elasticsearch operational. And during the duty, which lasts a week, they do not take the regular tasks. They take the maintenance tasks from our backlog of Elasticsearch tickets. Yeah, so that's how Elasticsearch is being operated now. Yes, so the last part, the discussion. Before going into the question phase, I would like to answer several questions up front. So I've described the lessons learned and the state of our installation. So the very obvious question is that is everything perfect with Elasticsearch now? And my answer is no. One reason is that I'm from Eastern Europe and and nothing is good enough for me. Another thing is the basic reality. One thing that is of concern is that Elasticsearch is resource hungry. As I mentioned in the previous slide, our Elasticsearch cluster, we have 3 Elasticsearch clusters, 160 data nodes each, meaning that it's a very big installation, very big deployment. Also, Elasticsearch version upgrades are still has to be checked before releasing into production. Our offline testing cluster helps with that. Like recently, when we wanted to migrate from Elasticsearch 7.7 to Elasticsearch 7.9, we've seen performance degradations. On a different note, our machine learning engineers still insist that Elasticsearch is not up for their tasks. This is despite the fact that the search ranking data is used for their model training, and their model is meant to re-rank the hits from Elasticsearch. This means that the re-ranking phase has to be done outside of Elasticsearch, meaning that we have other systems that handles that re-ranking step, and that adds to our operational complexity as an additional system in this query workflow. Also, the default Elasticsearch installation offers very few tools for us for the search relevance work, meaning that we have to either invent our own tools or just go and search for some additional tools from the industry. Yeah, and also from time to time we we contribute bug reports to Elasticsearch developers, because since we are having such a huge installation and all the little problems are immediately visible for us, so that we spot those. And the last problem was spotted like 23 days ago, and it was for version Elasticsearch 7.12, so very recent. Yes, so basically that was all I had for you today, and I'm open for the questions. So Alexander, can you help me with the questions?
Yes, absolutely.
If there are any.
Yeah, I didn't see any, but I can easily make up for that because I noted some down. One of the things I really liked is that you can see the whole evolution through the stack, like going from function scorer to distance feature, and it also makes sure you keep things upgraded. And one of the questions with regarding to upgrades is like, what is your upgrade strategy? How do you like orchestrate or execute upgrades? Because you have a ton of nodes. Like, do you do the classic rolling upgrade strategy, or is there any magic automation, including Ansible? Like, how do you run upgrades basically?
So our way to do an upgrade is a very simple one. So since we have 2 clusters of equal size, one is like our production cluster, another one is our mirror cluster. So what do? We take the mirror cluster, wipe it out, install the new version on those machines, index all the data to that new cluster, mirror the traffic to this new cluster. If it keeps up with the traffic with the decent percentiles, we just route the production traffic, wipe up the old cluster, and install the new version, is index the data and route the traffic back, so that we have this mirror traffic once again, just being a mirror. So that's our strategy basically. And since we have more clusters now, yeah.
So you have tooling in front where you can basically redirect your whole search traffic. I see.
Yes.
Okay.
Yes.
Okay, so now we have a question in the chat from Krupa. Did you set up any kind of auto-scaling as well, or do you have any findings there, or any reason why you didn't? I think it's more about like, are you able to reduce your traffic during peak times to probably save money or resources or something like that?
So two sides. We have product requirements that we don't want to break. So we don't do anything with queries. So as the queries go, it's problem on our side, on engineer side, to keep the Elasticsearch operational. So we do whatever it takes to keep the Elasticsearch operational. In terms of auto-scaling, we don't have auto-scaling, let's say, automatic, because we run everything on bare metal, and we manage Elasticsearch installation with Chef. And we tell Chef that those machines are dedicated for Elasticsearch, and that's it. So, and it takes time for add additional machines into Elasticsearch cluster, so that we provision Elasticsearch cluster of such size that would handle the query traffic, let's say, during the peak hours.
Yeah, that makes sense. Especially if you don't reuse the bare metal machines for anything else, it's probably just the safest route. You're going to go there.
Yes. Yes.
Okay. All right. Then we have a second question. How does the external re-ranking affect performance? And I think it might actually make sense to just be a little bit more verbose, just out of my curiosity, like what kind of re-ranking you're actually doing and why you do it. I think that just adds some more context here.
Yeah, so the re-ranking thing solves a problem. The usual search problem is that when you have too much things to show for your user. So basically, when the query is not very specific, and you have a million of let's say dresses to show for that particular user, the regular Elasticsearch scoring doesn't provide you that much of leverages to solve that issue. So we turned into let's say the click-through models, the buying metrics, all those engagement signals, to come up with a model that can, let's say, take the deep hits from, I don't know, from first 1,000 hits of a query, and then re-rank them based on the model that we built from the previous hits. And what this adds to our, let's say, query latency is that we have a kind of a hard limit of not allowing this re-ranker to take more than 150 milliseconds. And well, since it's kind of a hard limit, that falls back to the regular Elasticsearch ranking. And in numbers, well, the re-ranking adds around 100 milliseconds at P90 something, the last time I checked. So that's that.
Yeah, I think you're basically running into a classic e-commerce problem, like when you have a lot of choice what to show to the user, because the user doesn't want to enter a query, right? Like even though everyone thinks you want to have a Google experience, no one wants a Google experience if they search for stuff. They start with a simple search, and then you have to help them drill down.
Yeah, the very usual situation. I would say the book example.
Yeah, exactly. Yeah, it's I had the same. I ran an e-commerce shop with Elasticsearch like 10 years ago, and it seems the problems have not really changed. Just the solutions are luckily getting slowly better in there. Slowly. Yeah, I saw you already dealt with you already dealt with index sorting, I think. So you're not running it in production because apparently you found issues. But is it something you plan to switch to?
We are constantly actually trying index sorting either on one argument or another. One of the biggest wins in terms of scaling that I haven't mentioned in the presentation is that we have indices that are feature focused, meaning that we index the same data in several indices, and we route specific types of queries into those indices. And for those feature focused indices, we turn on ranking, not the ranking, but this index sorting just check if it helps from time to time. And from time to time, as seen in the slide before, we find some problems there. So for some queries, it is enabled, but not for everything, because not everything, let's say, benefits from this additional overhead during the indexing time.
Yes, that indeed makes sense. Yeah, and also one more question I had when you talked about in the beginning that you simply switched the data type from integer to a string. Was it that simple, or do you have some sort of fancy migration process in place for these kind of tasks?
We have a tool called Elasticsearch Index Management that we wrote ourselves. That among other things that it does, let's say it helps to create index templates in Elasticsearch cluster. And so we just changed the template, let's say, mapping. And then we did this dance that I described before with an offline cluster. We wiped it out, made the index templates, indexed all the data there, because the number, we don't have to change the data, the upstream data, in order to index it either as an integer or a keyword. So it was just a regular thing. We indexed the data up, we moved the traffic, and we see that the percentiles in this new cluster, bam, went down. So that was the story.
Still probably requires some syncing because your application needs to change the query it's sending, right?
No, for this case, it doesn't need to change the query it's sending, because it's the same terms query, the regular terms query.
Oh yeah, I remember. You used the terms in the range query for that one.
So
yeah,
no changes in query.
Yeah.
That was a party time.
Let's just hope you keep to have those changes without having to change anything in your application. That's a great change, actually, then.
Yeah.
So there's another question from Krupa. If you ever have compared Elasticsearch performance to Solr?
Since Elasticsearch is installed at Vinted so long time ago, and there were no people familiar with Solr and no setup for Solr, no nothing, we haven't considered Solr and we haven't measured it against it. So all our work went into making Elasticsearch operational for the workload that we had.
So Krupa is taking the opportunity for more questions. It's fine, don't worry about it. So how often do you end up using the offline or backup cluster and does it seem to justify the cost and maintenance?
Well, it definitely justifies the cost of maintenance, because during the October we had a couple of say weeks where most of those optimizations that I've talked before were implemented actually, and during that time it was such a situation that one cluster was not able to keep up with the query traffic during the peak hours. So what we did, we just split the traffic between those the main cluster and the so-called mirror cluster during the peak hours, so that Elasticsearch will not fall down. So for those couple of weeks, it was purely operational.
Yeah, I think it's always hard to justify the cost of something if you don't need it unless you need it. It's the classic cost fallacy here, I guess. But it's a good point. Also, the infrastructure you have in place to redirect and split and shadow the traffic, I suppose this is all self-written, or do you just sit on top of, I think there's some Go tool which allows you to do that, some Go proxy, but I suppose all of that is written by yourself?
So the short answer is that most of the stuff is written by ourselves. But if you want to check the details or to learn a bit more about what's in our Elasticsearch infrastructure, you can go to Vinted Engineering blog, and we are releasing we already have four blog posts detailing the things that we worked on Elasticsearch during the last year. So yes, most of the stuff is written by ourselves, and we have a zoo of tools there.
Yeah, who doesn't? Let's put it that way. Cool. So let's give it another 30 seconds or something to wait for more questions. Is there, to give you a chance to rant and vent, is there anything where you say like, this is absolutely not working as expected, or we really need to improve on that one, that you found during rewriting, changing your queries or anything like that, where like this is a point that is our biggest pain point right now?
I don't know. The biggest pain point right now is how to introduce changes so that we don't break the product requirements. So, like for example, we don't use text scoring. BM25 is not a thing in our querying. So how can we introduce such a changes without making too much fuss in the from the business requirements point of view? So that's a big headache, and Elasticsearch does not really provide anything for it. We do use the rank API in some hacky ways to measure if there is any like what's the impact, but it's also our custom made code that is not very precise.
Yeah, have you already taken a look at the vector field?
Not yet. Well, of course, I've tried it some time ago on my laptop, and when I learned that the vector field for the smallish dictionary takes I don't know 300 milliseconds to 1 second to respond to simple word to vec arithmetic, it was just not operational. It's impossible to deploy such a thing with our strict requirements. Like 150 milliseconds, anything above 150 milliseconds is considered an error. So
yeah, that makes sense in that kind of environment. Also, like there's some work going on right now on Lucene, not on Elasticsearch, to add an initial ANN API, which you might have seen already. I mean, it still kind of suffers from the problem that it needs to reconstruct the data structure when the Lucene segment merge is happening, and so some more work needs to happen in the background. But let's see where that takes us. There's tons of discussions from different engineers from a ton of different companies who try to settle on a generic implementation. Maybe that one will happen in the future there.
I'm following that discussion, and it's for more than a year for sure in the works. I mean, in this Lucene.
Yeah, there is an initial implementation, I think, in the Lucene 9 branch, which might be the master one right now, which you can play around with, but it's still in like super early discussion. So I wouldn't put anything of that in production, to be honest.
Yeah, and since we have 360 million documents, it will fall off. Yeah.
That's a real point there. All right, so we don't have any further questions. I think that was a great session. Like finding all the tiny little things and see how they break can be, well, enlightening and frustrating. So I'm rather happy you found your way through most of those, but I'm sure you will find some more. So thanks a ton. And to anyone else listening, if you want to rewatch this, we will put this on YouTube in the next couple of days. So you can check the Elastic YouTube community channel and just take a look over there. And yeah, that's that. Do you have any final words you want to like tell, get rid, or anything else?
Yeah, so just a regular thanks for my employer for giving me the opportunity to work on hard problems. Thanks Elasticsearch, and thank Alexander for hosting me this evening.
Sure thing. All right, everyone, have a great evening.
Yeah, have a nice evening all. Bye.